part of our intent is to get to the review questions and practice problems that you've been doing for homework. And we've covered the material for that in advance of that work, but still you haven't, right now you may or may not know whether or not you got it right or not. And part of being ready for the exam is knowing that you did it right, or if you did it wrong, what it should have looked like. So that's why beginning on Monday, we will be going through all the practice problems and all the review questions to make sure that if you were incorrect, you have a correct understanding of the material in preparation for the module exam, which may be on Wednesday or Thursday, probably Thursday, okay? So, quiz was on table 2.2, and just to go through that we're not going to go over that real quickly because we did that already, but it's just the prefixes 1 through 10. And why is it significant that we know the prefixes 1 through 10? Yes?
So when we name compounds, we know like how many there are.
Right. In the naming paradigm, you need to know the prefixes to indicate how many of each one of those atoms are in that particular molecule, right? But which of the two naming paradigms? We have two of them, don't we? What are the two naming paradigms? The first one was for, go ahead.
Is it ionic?
The first one was for ionic compounds. And remember, for the ionic compounds, we're going to name the molecule just going from left to right. Again, that's assuming that the chemical formula is written correctly, appropriately. So we'll assume that when we give them to you, they're appropriately written. You're going to go from left to right. And the paradigm is that the metals are going to lead if there is a metal. So when you name an ionic, first of all, you have to find out whether or not it is ionic. And we know it's ionic because it contains a metal. And it contains a metal because when we look up that element on the periodic table, it resides on the left-hand side of the jagged line with the exception of hydrogen. Hydrogen is it's in its wrong neighborhood. Okay? Remember, hydrogen should be over there on the right-hand side. So if it has a metal in it, it should lead the formula. So if we're checking whether or not a compound is ionic or covalent, we should know after we check the first element. Now, I go through and scan it all just to make sure that under another paradigm, another way of writing, there might be another metal in there. But for our class, for the vast majority of cases, I can't think of an exception right now, they're going to lead with the metal. So check the first one. Is it a metal? No. Then you're probably dealing with a covalent molecule. If it is a metal, it's ionic. And then all you're going to do is read the chemical formula by saying the names of the elements from left to right, and then adding an ide, changing the last element to an ide, to its ide name from table 2.1. Okay? We did that yesterday, and you all seem to get that pretty straightforward. The second kind of naming paradigm was the covalent molecules, or the covalent compounds. And it's the same idea, starting from left to right, except covalent naming needs more information than ionic. And why is that? Why do we have to have the mono, di, tri, tetra? Why do we need those prefixes in a covalent naming but not in an ionic naming?
Is it because an element might show up twice in the formula?
Not that it might show up twice in the same formula or that's written, but that the deal is for ionic compounds, the elements can only combine in that way. There is no other formulas that can be made. They always combine in a specific ratio, like 2 to 1, 3 to 2. The formula is always going to be the same in ionic. And we'll explain why, and you'll understand why very soon. But on a covalent, for this point, just remember that the fact that I've got carbon and the fact that I've got oxygen, there's more than one molecule I can make from carbon and oxygen. But if I have sodium and chlorine, it's going to make sodium chloride. That's what it makes. That's all. The NaCl. It doesn't make Na2Cl. It doesn't make NaCl2. It only makes NaCl. So I can name it sodium chloride. That's the only thing that those two elements combine to make. But for carbon and oxygen, I can make carbon monoxide. That's 1 carbon and 1 oxygen. I can also make carbon dioxide, 1 carbon and 2 oxygens. And because I can make more than one compound from those two elements, I need to have more information to say which one is it. So adding the prefixes before each element name, if we saw it written out as a formula, we would take the subscript, the small number, convert it into your prefix, and say it before the element. So we do that. And again, change the last name to an "-ide name. And the only other rule we need to remember is the exception that a subscript of 1 would be mono, but we never start the chemical name with a mono. So if it's a leading mono, just like we said leading zeros when we did signifigs and precision, like the leading zeros, you understood that that meant zeros at the left with nothing else in front of it. So when you write out your chemical name, your chemical should never start, your compound, if it's covalent, will never start with a mono. If it's a mono, you drop it. Now if it's a mono inside of the molecule, like if there's another element in that molecule that only has one of them, you have to say the mono. The only time you drop mono is when it's the first, when it's the lead element, you drop the mono. Okay? Any questions on the ionic and covalent naming paradigms? Again, that's review from what we did yesterday. We're going to push on to this final comment. Please understand that what we've done here for naming is a very simplified, it's a very limited discussion. It's very basic. It's for the scope of this course. But there are more exceptions, there's more paradigms, there's higher complexities. That's why I say at times you'll see something that's written that doesn't look quite right. And I can tell, for example, sometimes you're going to Google for answers and you're going to write it down in the wrong paradigm. As a matter of fact, there's a question in the next module, well, I will know who are the Googlers. Because the question asks for some information, and the same terms exist in other fields. What do I mean by that? Like, we're going to talk about a couple terms next module, and those terms are used in chemistry, but they mean something very different when you talk about psychology. And so when you Google it, if you just write down what you find on Google and don't think about it, I will get your psychological answer, or maybe your legal answer, or maybe your sociology answer, and it won't be a chemistry answer. So, just so you know. And we also didn't talk about common names very often. This dihydrogen monoxide, in your mind, what is that? Dihydrogen monoxide. But you call it H2O, right?
Water.
Water, right. So, common names, when you say things like water, water is a common name for dihydrogen monoxide. We might say water, assuming that you know it's H2O, assuming that it's technically dihydrogen monoxide. Okay, so if somebody says, would you be willing to drink a liter of dihydrogen monoxide? Of course, yeah, I would, because it's water. One other thing while I'm talking about water, we know that something is ionic because when we dissolve it in water, it conducts electricity. I didn't emphasize that point through the text, and it struck me last night, but you realize, of course, that pure H2O does not conduct electricity. You know, you hear all the time about making sure that you don't put electrical current into the tub or into the pool because you'll get shocked and you'll die. Pure H2O does not conduct electricity. What conducts electricity are the ions that we put into H2O. Pure H2O, as pure as we commonly use, is called distilled water. You can buy it at the store. You use it maybe for making coffee, because distilled water, when you run it through systems, it doesn't leave behind that crud, the lime and calcium buildup. It's actually that lime and calcium buildup and other ions like that which conduct electricity, not the H2O. So pure H2O, if you're in it, you can put electrodes, drop a power line in it, you're going to be fine. Because it doesn't conduct electricity. But it's really difficult to find H2O that doesn't have other things dissolved into it. As a matter of fact, if you were drinking H2O that had nothing else in it, you would hate it. Why do you think you drink sports drinks? Right? Because you physically know you need the electrolytes, or because you like the sugar and the salts and all the other ions that are in it? It's those salts and ions, it's those things that are dissolved in the water that give it the flavor. You drink pure water, you feel it, but you don't taste it. There's no taste to it. So when you taste water, and you've done that before, right? You've had, I like that water better than this water. It's not because of the H2O, it's because whatever's dissolved in the H2O. And the stuff that's dissolved in the H2O is stuff that'll kill you because it conducts electricity. And that's why we say, if I put something in solution and I stir it up and it conducts electricity, because in pure H2O, it wouldn't until you put something in it. That's an important thing for you to remember. Okay? So that's kind of not in sequence, but I wanted to make sure you had that as part of your thinking about conducting electricity. It's not H2O that conducts. It's what's dissolved in the H2O that conducts. All right, moving on. classifying matter. We're almost done. This is the last planned day of new content for this module. We're going to finish it right now. So we've said that everything exists as either an element or a compound, right? In the book it says everything we see. It's even bigger than that because it's the air around us, right? The air around us is either as forms of elements or compounds. We're going to find out later that virtually all of them are compounds. But everything that's made up of matter exists as either an element or a compound. Now we're going to get a little bit more specific on, okay, what kind of samples do I have? What kind of classifications are there? There's two different ones, two broad general domains or two broad general categories of either pure substance, which is a substance that contains only one particular element or one particular compound. So what I'm talking about here is if I have a sample, if I have a handful of powder in my hand, I could have a sample, a handful of, let's say, calcium. If I have a handful of calcium, then hopefully you understand that that means that every single atom in my hand is an atom of calcium. Okay? For it to be pure, everything has to be the same. So if it's calcium, that means everything is calcium. If it's sodium, it means every atom is sodium. Now that would be two elements, right? It could be I have a pure sample of sodium chloride. I've got salt. Or maybe sugar. Those aren't elements. There's no periodic position up there for salt or periodic position for sugar because salt and sugar are made up by combining elements to make compounds. But if I have a sample in my hand where every single piece in my hand is a molecule of salt or is a molecule of sugar, then I also have a pure sample. Because everything in my hand is either the same element made up of the same atom type, or it's the same compound, which means every single molecule is the same. Okay? That's a pure. So what would be the antithesis of pure? What's the opposite of pure? We're not going to say impure. Okay? It's a mixture. A mixture means that everything in my hand is not the same. I have a mixture. So if I have some potassium and some sodium in my hand, and I have a powder that I mix up, I no longer have a pure substance. I have atoms of sodium and I have atoms of potassium, but in my hand, is it pure sodium? No. Is it pure potassium? No. It's a mixture. Or let's say that I have in my hand, I have taken salt and sugar and I've mixed it together. Okay, when I had pure salt and I had pure sugar, it was a pure substance. But when I bring them together, now no reaction has taken place. All I'm saying is these molecules get close to each other, or in the first case, those atoms get close to each other, and they don't react. They stay as whatever form they were in. So in my hand, I have different structures. I have different molecules. In my example, sugar and salt, or potassium and sodium. So if everything in my sample is exactly the same, whether it be an atom of an element or a molecule of a compound, if everything is the same, it's a pure substance. And if there's differences, if there's different types, it's a mixture. Is there anything difficult about that concept? Because we're going to build on that real quickly here. Okay, no response. A little bit of bobble. Get it? Okay, we're moving on then. So, for example, pure substances. If I have a sample that's 100% iron, every atom in my hand is an atom of Fe, of iron. Then it's pure. And if every molecule in my hand is sugar, it's pure. However, if I have iron and sugar mixed together, they don't react. If I were to go on Frizzle's bus and go right down in there, I would find iron atoms and I would find sugar molecules. They're next to each other, but they're not reacting. I know then I have a mixture because there's differences between the structures in my hand. And if you take something and you dissolve it in liquid, like the case of dissolving sugar in water, guess what? It's a mixture because you're in the water. It's an aqueous solution, it's called. But if you dissolve something in water, then that substance is in the liquid. Or if something is dissolved in any liquid, suddenly it's a mixture because you have something that's broken apart. It looks like it disappears, but here's the big deal. It doesn't disappear. It's in there. We've just put more space between all the different structures. And so it appears to disappear. But not everything in there is pure, one or the other. So it's either going to be a pure substance or it's going to be a mixture. So if you look at figure 2.6, it's on page 70, real quickly. My original slides had this all up here with nice arrows pointing to everything. It was pedagogically really well done, but we'll just deal with this flat slide here right now, okay? So look across, and I want to explain figure 2.6 across the top, and then we're going to walk across the bottom. On the top picture, what they show you there is sulfur, which is yellow, and iron, which is black, and it's all mixed together, okay? So the scientist or the person in the lab, they've got a mixture of black and yellow powder. The yellow is sulfur, the black is iron. Now, one of the deals is that with mixtures, you can separate out the different structures based upon the chemical properties of those structures. And this is a good example of that. If I have a pure substance, I can't separate anything out. But if I have a mixture, and in this case, let's say that we had this mixture of sulfur and iron, and I said, hey, I need you to go to the sulfur-iron mixture and just bring me back the sulfur. You're like, okay, how am I going to do that? Well, you could get on Frizzle's school bus and go down and push all the yellow to one side and all the black to the other side, and then come back to this dimension and separate it. But you know what? That's not real life, right? You know that's just a cartoon. So how can we really do it? Well, in this case, we've got iron and sulfur, and one of the properties of iron is it's magnetic. And so it's attracted to a magnet, and sulfur is not. And so the properties of the components of the mixture help us to separate them if we can find things that they have different, that there's a difference in them. In this case, it's magnetism. The iron is magnetic, the sulfur is not. So you see in the top center picture, as we pass a magnet through the mixture, the iron is drawn to the magnet. The iron is separated out. And you notice in the last picture, they're holding the magnet. It looks like that big puffball on it, right? That's all iron that's stuck to the magnet, and it forms a representation of the different magnetic waves that come out, or magnetic field that's around it. It's kind of cool. Okay? But the big point for this class and where we are in chemistry is that when you have a mixture, you can separate out the different components of that mixture according to their physical properties. So on the 2.6 across the top, the physical property we're capitalizing on is that iron is magnetic and sulfur is not. So I have a mixture of iron and sulfur, and I put a magnet through it. The iron is going to be attracted to the magnet, the sulfur is going to be left behind, and I can separate them in that way. Other things might be the size of the molecule. Maybe we'll put it through a filter, and one molecule is small enough to go through the filter, the other one is not. And so that we can separate it physically that way. That's another concept of what we're doing. Now, there's more technical, that's just a general idea, okay? The idea that if we have a mixture, we can separate out the parts of the mixture according to the unique physical properties of whatever's in the mixture. But notice on the bottom, in this case, we have sulfur and iron that were put together, just like on the top, sulfur and iron, but we added heat to it. And we added heat to it, we added energy to it, and the sulfur and the iron reacted and made this mixture, okay? This iron sulfide is formed, this black powder. But see, here's the deal. Just because iron sulfide is made up of iron and sulfur doesn't mean it behaves like iron or sulfur, or even iron and sulfur close to each other. Iron sulfide is something other than iron, and it's something other than sulfur. It's its own structure. It has its own properties. In this case, iron sulfide, though it has iron in it, is not magnetic. You see? And so that's why down below they pass the magnet through and nothing sticks. But you say it has iron in it. It does, but it's in a different form now. It's not iron, it's iron sulfide. And that molecule has its own properties, which are different from the components that make it up. Okay? So this also shows us on top and bottom. On the top, we have a mixture. On the bottom, we have a pure substance, right? Because everything there is iron sulfide. And so since we're not really trying to separate anything out, what they're just showing is that the molecule has different properties than the elements that make it up. So we have to know the characteristics of iron, characteristics of sulfur, and also characteristics of iron sulfide, if that's what we're trying to accomplish. Okay? So I've already done across the top and across the bottom, explained both of those. Last step. Let's say we've got a mixture. Given that we have a mixture, and that mixture means that we have a combination of different types of structures, we have two different ways we can describe it. First of all, there's a homogeneous mixture. Homogeneous. The prefix homo means the same. So think of it this way. We have a homogeneous mixture. That means that no matter where we look in it, it's the same. It's the same mixture. It's evenly dispersed everywhere. Okay? Means it's homogeneous. So a homogeneous mixture is a mixture with a composition that's always the same no matter what part of the sample is observed. And we'll give a couple examples in a moment to hopefully make more sense. But I've already said homogeneous means the same. Homo means same, so it's the same throughout. That's what a homogeneous mixture is. What we're saying is we've got more than one type of atom or molecule. So we know we've got different stuff mixed together, but for homogeneous, it's mixed evenly. No matter where I look in the sample, it's going to look the same as when I look someplace else. The opposite of homogeneous is not advancing. There we go. Heterogeneous. Hetero means opposite. You know? And let's just get straight to the point. We talk about, way to remember that, homosexual, heterosexual. Heterosexual, you have a fondness for the opposite. Homosexual, you have the fondness for the same. So homo, the same, means it's everywhere the same. Hetero means it's not the same everywhere, there's differences. So when I look at a substance that's heterogeneous, that means if I take a sample on one side and take a sample on another side and I compare them, they're not going to be the same. Granted, they're going to have different structures in them because they're a mixture, they're not a pure substance. But when I look at different places, there's something categorically different about them. And I think it's best understood by using these examples. For some homogeneous mixtures, salt water. Actually, let's use Coke as well. Now, let's assume it's the same temperature. There's a lot of different variables here, but here's the basic idea I'd like you to remember with Coke and salt water. When you pour a Coke, do you rush to get the first drink because it's always better than the third drink, which is always better than the fifth drink, which is better than the seventh drink? Or is Coke pretty much everywhere the same? Pretty much the same. I know that when you first open it, there's more carbonation and there's slight variations, and maybe you like it colder rather than warmer, so drinking it first because it's colder. But if it's the same carbonation and the same temperature, you take the first drink, you take the second drink, you take the third drink, and you're expecting it to be the same. It's not like, hey, take the first drink, and it's like Coke. You take the second drink, it's more like Dr. Pepper. You take the third drink, it's more like Diet Coke. You take the fourth drink, and you're like, this is paint thinner, okay? You know that if you had that kind of experience, that you're not drinking Coke, or something happened. This is not Coke, right? Salt water. There are reasons for there to be variances. But generally speaking, if you've got a glass of salt water, the first drink is not saltier than the last drink. It's the same. So that's the idea of having a homogeneous mixture. It's the same everywhere. And steel is the example of a metal that is the same everywhere. It's heated up to high temperatures, and then the things that make it up are blended together, and that blending process, when it cools, produces a solid, but that solid is consistent throughout, because when it's not consistent throughout, that's where cracks happen, that's where it falls apart. Okay? So they're very diligent on making sure that it's the same everywhere, which is why it's referred to as a homogeneous mixture. Yes, it's a solid, but if we go down to the atomic level, in steel, every atom next to every other atom is not the same. It's a mixture of things, okay? And I maybe sometimes use it interchangeably. Steel is not the same as iron. Iron is used in steel. Iron is one of the major components that make up steel, but they're not the same thing, and we sometimes use those terms interchangeably. Okay, steel is a mixture. Steel has carbon put into it, added to it intentionally, among other things, okay? So just think of it in terms of iron and carbon mixed together. That'll let you know it's not all the same molecule. We've got different atoms, Fe atoms and C atoms, carbons and irons, close together to make steel, and some other things as well. So, any questions on what it means for it to be homogeneous? The same everywhere. Okay, the other option would be for it to be heterogeneous. The classic example, the one I want you to bring to your mind all the time because it comes to my mind all the time, is the tailored salad dressing, right? You're the first one at the table. You give it a good shake. You pour it. You set it on the table. You eat your first salad. Time for the second salad. You put the lettuce on your plate. You reach over, you grab the Italian. What do? You shake it up again. Why? Because if you don't, it separates out. If you leave it there, it makes different strata. It has different layers. And you shake it up because you're attempting to homogenize it because you want a nice even blend. But the truth of the matter is, left to its own, it's going to separate out. And that separating out shows us very clearly that it is a heterogeneous mixture. It is naturally not even everywhere. Or maybe a bowl of cereal. I give you a bowl of cereal and say, is it the same everywhere? Well, if you got the cereal that floats, if you deep dive into it, it's all milk. If you go way up on the top, it's all cereal. You hit right at the surface level or maybe below because the top is pushing it down, you get a cereal milk mixture, see? It's milk below, it's cereal above, and it's cereal and milk in the middle. It's not the same everywhere, so it's heterogeneous. And icing, a cake with icing. Real simply, you get a piece of cake, you look at it. I always go for the corners. Why? I like the icing. I know that if I get a corner piece, I'm going to get more icing than any other piece. That tells you it's heterogeneous. But also, when I take a bite, every bite is not the same. I eat the cake out first because I'm saving the icing for last because it's not the same. I'm leaving the stuff I prefer for last. Okay? So if you can take a piece of it and it's not the same as another piece, it's heterogeneous. It's not the same everywhere. And this chart, figure 2.7 in your book, kind of breaks all that down, shows it in a nice graphic that, hey, everything that exists that has matter is either going to be a pure substance or a mixture. Those are the two big broad categories, pure or mix. Pure substance or mixture. If it's a pure substance, it's either going to be atoms of a given element or molecules of a given compound. All the same for it to be pure. And if it's not pure, it has to be a mixture. And if it's a mixture, it's either going to be the same everywhere, the same blend everywhere to make it homogeneous, or it's going to be blended with differences in other places that make it heterogeneous. So for example, an egg is a mixture. If you make scrambled eggs in a food processor, not with a fork, which isn't as good, but if you perfectly blend that all up, you could argue that that is a homogeneous mixture. But when you take an egg and dump it out, you've got the yolk, you've got the white, you've got the that becomes white, and all that kind of stuff. It's not homogeneous. If you make scrambled eggs, you could argue that it becomes homogeneous, but in its natural state, it is heterogeneous, yolk and white. And so, comment about milk. Milk from the cow is heterogeneous. I used to work on a dairy farm, okay? I know when you get the raw milk, we would let it sit, intentionally let cream come to the top, and skim off the cream because the cream was what tastes good. It's the milk fat. That's what we naturally like. Like ice cream, the higher the milk fat, the better. Well, if we skim off the milk fat, we're left with the skimmed milk, which people buy, right? That's milk without the milk fat. But what we do is we take milk, raw milk, which is heterogeneous, and we homogenize it. So if you've seen homogenized whole milk, what that means is they put it through a process where they mechanically and chemically work it so that when it sits in your refrigerator, it doesn't separate out. Because if it separated out, everybody would drink the first half of the gallon and nobody would drink the second half of the gallon because all the good stuff's gone by the time you get to the bottom. But they homogenize it so it stays mixed together so the first glass is almost as good as the last glass. See? So that's a forced homogenization of a heterogeneous mixture. And air, the air we breathe. Now, if you were to take air and remove the humidity, which is the water vapor that's in the air, take that water vapor out, air is 78% nitrogen, 21% oxygen, and 1% other gases. Okay? So it's a mixture. The nitrogen isn't reacting with the oxygen. These are molecules that are close together, but they're not reacting. And it's also something you need to see right here real quickly. Nitrogen is the largest by percentage molecule in our air. The neat thing about nitrogen is it's inert. It means your body doesn't use it. It's a thinner. And so what God has done is we need oxygen, but we don't need pure oxygen, because if you have pure oxygen, you hyperventilate. You got to stick the bag over your head and breathe back your carbon dioxide. And if we have too little oxygen, we become hypoxic and we faint, we fall out. What God has done is given us 78% inert gas. We breathe it in, we breathe it out. Our body doesn't take it, doesn't use it. It like transports the things we need, transports the oxygen. But it's in the perfect proportion for what we need to keep us both alive and to keep us from hyperventilating. Keeps us from becoming hypoxic and keeps us from becoming hyperventilated. By God thinning it out with 78% nitrogen.